Hi everyone. Welcome to another video by Cheenta. I am Rajdeep, and this is episode 3 of this number theory series that we've been cutting for a while. Today we'll continue our discussion on prime numbers that we briefly started last time. We'll see essentially how many prime numbers there are, how to think of them, how to process them. This video is going to be about primes. At the end of this, I will essentially give you a reason to care about the next step in the process, which is congruences. Modular arithmetic, in general, is an incredible tool, and I'll give you a problem at the very end of this video, which will give you one of the many reasons we care about modular arithmetic and why it's so nice. But this video itself is going to be about primes. Hope you enjoy. So let's get into it. So to quickly recap what we saw last time, a prime number is a natural number more than one, of course, which has no factors other than 1 and itself. We saw some examples last time. 2 was an example, 3, 5, 7, 11, and so on. Alright? So this is what a prime number is. A number is not prime if it's composite. It's just a name. Alright. One of the things we saw last time was the fundamental theorem of arithmetic. It said that any natural number n can be written as a product of prime powers, right? All the PIR primes in a unique way. Right? This is what we saw last time. So this is recap. Today we'll answer the question mainly. That's one of the problems we'll look at, is how many primes are there? Right? This is the first question we'll address. Other than this, one of the things we'll look at is thinking of numbers, natural numbers, as multi-sets of primes. This is more than anything a way of doing number theory, a way of thinking about numbers. It's a short section, and we'll see an application of this in how do we think of the GCD and LCM in terms of primes. So this is okay. In how many primes are there, we'll answer a few more questions. I'll take a short digression on the next question. Once this is done, there's a deeper questions that we can ask, stuff that's still somewhat unsolved. I'll even hint how the famous Riemann hypothesis ties into all of this. But this is all trivia. For us, these are the big questions. So I want to first talk about this. Because of the fundamental theorem of arithmetic, I can think of any number as essentially a collection of primes in a unique way. And a multi-set of primes, or a multi-set in general, is really just a set where we drop the condition that one element cannot occur more than once. So, for example, the number 4 corresponds to the multi-set of primes 2, 2. The number 12 corresponds to the multi-set 2, 2, 3. Why? Because 12 is 2 into 2 into 3. So every natural number corresponds to a unique multi-set of primes, right? So that's really just a way of thinking about numbers. Whenever you think of a natural number, one of the things, there's something you can always do, and many a times in problem solving, it's incredibly helpful to think of a natural number as just a bunch of primes put together. That it helps immensely in many problem solving situations. And it's a way of doing mathematics, in particular number theory. One of the immediate applications of this is the GCD and the LCM. If I think of what the GCD is, so if I have a number A, which is some P1 to the A1 all the way up to Pk to the Ak, and a number B, which is, so I'm going to make a jump here and I'll justify it in a bit, which is P1 to the A to the B1 all the way up to Pk to the Bk, where these Pi are the same primes. How can I do this, you say? For example, if I take the numbers 6 and 5, 6 is 2 into 3, and 5 is just itself. Clearly, the set of primes is different here. What I do here, in this case, to make our lives easier, is add the condition, or rather drop the condition, that the AI need to be natural numbers. I let them be 0 as well. Essentially, I can have a uniform discussion of what primes are involved. So under this caveat, rather dropping off caveat, I'll write 6 as 2 to the 1 times 3 to the 1 times 5 to the 0, and 5 as 2 to the 0 times 3 to the 0 times 5 to the 1. Okay? Now let's think about GCD, or for that matter, divisors are in terms of primes. If n is a number which is P1 to the A1, Pk to the Ak, and if D divides n, really all the primes that show up in n must show up, or rather not must, but will show up in some capacity in Bn. So if I think of n as this multi-set of primes, Dn, our divisor D, is really just a subset, a sub-collection of the primes that show up in n, right? So, and this is again because of the fundamental theorem of arithmetic, that if a prime shows up in D, it will show up in n, because it's all multiplied. Because D divides n is the same thing as saying n is D times something. So whatever primes are here in D, they'll also be in n, perhaps to a lesser exponent. So what this tells me is that if n is P1 to the A1 up to Pk to the Ak, that implies that every divisor T, right, is of the form P1 to the, say, A1 prime, P2 to the A2 prime, all the way to Pk to the Ak prime, where each of the AIs are between 0 included and AI included. So AI has made a, hopefully that makes some sense. So for example, if I have the number 2335, the natural number this corresponds to is 90, right? Think of any subset of this. If you consider the empty subset, Phi, that corresponds to 1, right? You take no primes. You consider this subset, 33, that corresponds to the divisor 9. If you consider this subset, 35, that corresponds to the divisor 15. Hopefully, you see the picture here. Every divisor is really just take all the primes, how many ever times they occur in n, and just take some sub-collection of them. That's what every divisor is. So, we have this. Now if I have A, coming back to our original form, if I have A, which is P1 to the A1 all the way up to Pk to the Ak, and B is P1 to the B1 all the way up to Pk to the Bk, a common factor of A and B, right, is a number B such that it's of the form P, obviously since D divides A and also D divides B, it's of the form P1 to the, say, alpha 1 all the way up to Pk to the alpha k, where the alpha are not only less than A1, they're also less than B1. So they're less than equal to both A1 and B1. In particular, it's less than the minima of A1 and B1 and more than 0. So AI and BR and that. AI and BR. So this divisor, any divisor, common divisor of A and B is characterized like this. It's P1 to some number less than equal to the minimum of AI and BI, but each of the primes. So what is the greatest common divisor? Just have the greatest possible exponent, which is P1 to the minimum of A1 and B1, which is the max thing you can allow, making sure that whatever number you're looking at is a common divisor. The exponent that you can raise P1 to must be less than the exponent that occurs in both A and B. So that's the minimum. That's the max you can allow. The same goes for any other prime. Right? Let's take an example. Let's take 15 and 24. 15 is 3 to the 1, that's 5 to the 1. 24 is 2 cube into 3. So if you want to write them in a uniform way, it's 2 to the 0 times 3 to the 1 into 5 to the 1. And this is 2 cube into 3 to the 1 times 5 to the 0. Take the minimum at each level. That's be 2 to the 0, 3 to the 1, 5 to the 0. So the GCD is 3, which you can verify using any of the other methods, including the Euclidean algorithm, which we saw last time. This gives us one of the ways of thinking of the GCD, and divisors for that matter. What about the LCM? By a very similar argumentation, where instead of having primes, instead of not having primes, we have as many primes as possible. A multiple of A, which is P1 to the A1 all the way up to Pk to the AK, is some number B. So if I look at a multiple B of A, rather let's say TA multiple of A, that will obviously include all of these guys to their maximum power and more, of course, right? Because P to the A obviously divides P to the A plus 1 or A plus 5, whatever. So it's P1 to the B1 all the way up to Pk to the Bk, any multiple of A, where the Bi are at least AI. So the ordering has to, and you can have extra primes. Right? So if I have two numbers A and B, and I write them in the same form as before, P1 to the A1, Pk to the AK, and B as P1 to the B1 all the way up to Pk to the Bk, where I've done the same thing, where whatever primes are missing, I just write them as that prime to the 0. The LCM, by this argument, I don't want any extra primes. Obviously, that's bad because the LCM is the lowest common multiple. I don't want anything extra. That will be P1 to the max of A1 and B1, P2 to the max of A2 and B2. I obviously need at least this much power of P1 because I have to satisfy the condition that every multiple of A has exponent of Pi more than AI. Hopefully take a second there to process that. But yeah, the LCM is P1 to the max of A1 and B1, P2 to the max of A2 and B2, all the way up Pk to the max of AK and Bk. Again, you can take an example, see that everything holds up. This also gives us very quickly the proof of the fact that GCD of A and B times LCM of A and B is the product of A and B, right? Because at each step, if you have P1 to the A1, P2, all the way up to Pk to the AK, and same thing for B, you're kind of choosing one number between A1 and B1 for the GCD and the LCM. So for P1, it's like, say A1 is less than B1. So in the GCD, you'll get P1 to the A1, and in the LCM, you'll get P1 to the B1. The same thing happens. So when you multiply it all together, GCD times the LCM is just P1 to the A1 plus B1, P2 to the A2 plus B2, Pk to the A2 plus B2, AK plus Bk, which is what? It's just A into B. That immediately proves us this. So this is the power of thinking of numbers and divisors in terms of primes. It's a very potent idea. All right, good. So that concludes our section on thinking of numbers as multi-sets of primes and so on. So quick note, and this is something you can find in the wonderful book, Modern All-Paired Number Theory by Aditya Khurmi. This is a viewpoint that's really exponentiated in that book in the first few chapters. So it is in this book that he writes the GCD as really the intersection of the two multisets involved. If the number A corresponds to the multiset, some sort of multiset, and primes are sitting inside here, and B is another multiset with some more primes, some other primes sitting here, the GCD is actually the intersection, right? It's all the things that are common to A and B, right? Similarly, the LCM is actually the union of the multisets involved. So you can try and verify this idea, and it only clarifies further the notion that primes kind of form the atoms of the natural numbers. Okay, cool. Let's move on to the next part. How many primes? So we've defined prime numbers, we worked with them. You can obviously ask the natural question, how many primes are there? So Euclid, a famous mathematician from Greece, ancient Greece, proved that there are infinitely many primes. And we'll see Euclid's proof shortly. There are many, many ways of proving that there are infinitely many primes. In fact, one can show that there's infinitely many ways of doing that. Really, all you need is a sequence of numbers such that any two elements are co-prime. And maybe that's something for you to think about. One of the ways it's done is by using the sequence of Fermat numbers, right? Which I haven't defined yet. You can look them up. Fibonacci numbers, for example. Any two Fibonacci numbers are co-prime. Something to think about. And so the Fibonacci sequence is infinite. So you pick up infinitely many sequences, infinitely many primes. That's one of the ways of proving it. Whenever you have a sequence like that, you get a proof. But this proof is a proof by contradiction. So say there's only finitely many primes. P1, P2, all the way up to Pn. Say this is all of them. For the sake of contradiction, say these are all the primes. What we'll do is, we'll construct a number that none of these primes can divide. So a new prime has to occur. That's it. Consider the number P1, P2, all the way up to Pn plus 1. Can any of the primes P1 to Pn divide them? Say Pi. If P1 divided this number, since P1 divides this number, it will also have to divide 1, right? Two multiples of a number must be at least that number away. Which implies, I'm using that fact that we proved earlier, that if D divides A and D divides B, then D divides D minus A or B plus A for that matter. That's what I'm using here. To get that, since Pi already divides this and Pi divides this, I get Pi divides 1. Can't happen. So none of the Pi's divide this new numbers that I've created. What does that mean? That these can't be all the primes. Thanks to the fundamental theorem of arithmetic. There must be a prime sitting inside n, and it can't be any of these guys. So there must be more primes than that. So this proves that there are infinitely many primes. A homework that I'm assigning to you guys at this point is the following. Prove that, well, part 1, every prime number is either of the form 4k plus 1 or of the form 4k minus 1. By which I mean, it can be written in this form. Every prime number is either 4 times some natural number plus 1 or 4 times some other natural number minus 1. 5, for example, is in this category. And 7, for example, is in this category. It's 4 into 2 minus 1. So, well, first show that that's the case, and then show that, using perhaps a very similar argument to what we just saw, that there are infinitely many primes of the form 4q minus 1. That's homework for you. The trivia that I promised initially about how many primes there are has to do with the prime counting function pi of x. This pi has nothing to do with the constant pi, which just counts how many primes there are until the number x. So this is further making quantitative the question how many primes there are. I know there's infinitely many, but how densely packed are they? How many? If I go up till 100, the number 100, how many primes will I see? If I go till 1000, how many primes will I see? This is about the distribution of primes now. Sure, there's infinitely many, but there's infinitely many squares, and there's infinitely many cubes, and there's infinitely many natural numbers. Clearly, squares occur less frequently than all the natural numbers, well, which occur all the time. Cubes occur even more scarcely, and so on. So how many prime numbers there are until the real number x? It's kind of like starting at, say, 1, going till x, and asking how many prime numbers you spot on the way. There's a famous theorem called the prime number theorem, which has been proved. It's a wonderful proof in the distribution of prime numbers. It was first guessed by, among other people, by Gauss, and he was one of the first people to try to prove it. And it says that the function pi of x grows like x by log x. Right? So in particular, the fraction pi x by x, the fraction of numbers until x, which are primes, is inverse logarithmic. Well, this is not exactly specific. Neither is this. This can be further clarified. Where does the Riemann hypothesis come into this stuff? In a way that I will not get into right now. There's obviously the question of, sure, pi x may be approximated by x by log x. How good is this approximation? There's obviously some error term, right? Because, well, x by log is a continuous function. It can't match perfectly with pi x, which is a discrete function. This error term has to do with the Riemann hypothesis. The Riemann hypothesis says something about the zeros of the Riemann zeta function. If the Riemann hypothesis is true, it will give us a very, very nice and in some way the best possible error term. You can't do better than that error term. The Riemann hypothesis is currently unproven. It's one of the famous millennium problems. Anyone who solves the Riemann hypothesis gets $1 million. You can think about it. But yeah, the Riemann hypothesis kind of gives us, if true, the Riemann hypothesis would give us the best possible error term on the prime counting function. That is all for today's theory. What I leave to you is the following question. You may remember the divisibility rules from high school. That a number n is divisible by 3 if the sum of its digits is divisible by 3. Same for 9. And something similar for 11, where you consider the alternating digits, sum them, look at their difference. Why don't you try to prove this result? I guess you've not seen a proof. And if you have, great. But if you haven't, why don't you try to prove it? You've learned a little number theory at this point. Try and prove it. We'll see in next class that modular arithmetic gives a very nice way of thinking about these things. That's it for today. I'll see you in the next video, and you have some things to think about. There's a homework problem. Have fun solving it. Bye-bye.